How do you actually teach a computer grammar? Something we humans do without even thinking about it. Well, it turns out that's one of the biggest challenges in AI. And the solution? It's a really cool process called part-of-speech tagging. I mean, think about it. For you and me, language just happens. We read, we talk, we get what other people are saying. We're not sitting there consciously thinking, okay, that's a noun, that's a verb, and that's an adjective. It just feels totally automatic, right? And this is the key thing, what's so easy for us is a giant, massive puzzle for a machine. I mean, how can a computer possibly figure out the difference between a noun and a verb when all it sees is just a bunch of letters in a row?
Okay, to really get what I'm talking about, check out this tiny little sentence. They can fish. Simple, right? But is it? Is can a verb, like they are able to fish? Or is it a noun, like they're putting fish into a metal can? And what about fish? Is that the action of fishing, a verb, or the animal, a noun? See? That confusion, that ambiguity, that's the core of the whole problem.
So yeah, that ambiguity, that's really the hidden challenge in all of language. A simple sentence like that one just pulls back the curtain on how complex this all is. And the key to cracking that code is this process we're talking about, part-of-speech tagging. So what is it exactly? Well, you can think of part-of-speech tagging, or POS tagging, as basically going through a sentence with a digital highlighter. For every single word, the computer attaches a label, noun, verb, adjective, and so on. It's almost like we're teaching the computer how to diagram a sentence, like we did in school, so it can finally see the hidden grammar underneath. And you might be thinking, okay, neat trick, but why does it matter? Oh, it matters a lot. Because this process is the invisible engine behind so much of the tech we use every single day. When a search engine actually understands what you're asking, that's POS tagging. When a chatbot can have a conversation that makes sense, that's POS tagging. It's the grammatical scaffolding that holds all of that stuff up. All right, so how did the pioneers first try to tackle this? Well, they went with the most logical first step you could think of. If a computer needs to know grammar rules, well, let's just sit down and write out all the rules of grammar by hand. And the idea was pretty simple, really. First, you build a huge dictionary of words and all their possible tags. Then, you create a massive, and I mean massive, list of rules. Simple things like, hey, if a word ends in Y, chances are it's an adverb. Or, if a word follows the or a, it's probably a noun. It's a very human-centric way of trying to solve the problem.
But as you can imagine, this approach had some major pros and cons. The big advantage was that it was totally transparent. You could literally open up the code and read the rules the computer was following. But the downsides? Whoa. The manual effort was just astronomical. And the rules were so brittle. The second they came across slang or an exception to the rule, which language is full of, the whole thing would just break. So that led to a really clever evolution. People started thinking, okay, instead of a human writing thousands of rules, what if the computer could learn the rules itself? And that's where transformation-based tagging comes in. Here's how it works. The system makes a first, kind of rough guess at tagging a sentence. Then it looks for its most common mistakes and automatically creates a new rule to fix that one type of error. And it just does that again and again and again, basically writing and refining its own rulebook as it goes. But even that wasn't quite the answer. The real, honest-to-goodness breakthrough, the paradigm shift, came when researchers stopped trying to teach the computer the rules of grammar and instead just let the computer discover the patterns on its own from tons and tons of data. This was the beginning of the statistical revolution. And really, this was a fundamental change in philosophy. The whole question shifted. It went from what should this word's tag be, according to a grammar textbook, to looking at millions of sentences. What is the most probable, the most likely tag for this word right here in this specific spot? It stopped being about rules and started being about probability. Now, the workhorse of this new statistical era was something called a hidden Markov model, or HMM. It basically boils down to calculating two key probabilities. First, there's the transition probability.
That just asks, how likely is a noun to show up after, say, the word the? Then you have the emission probability, which asks, how often is the word fish used as a noun versus a verb out in the real world? The HMM just chains all these little probabilities together to find the single most likely sequence of tags for the whole sentence.
But NNMs had a kind of tunnel vision. They were great, but they really only looked at the word or the tag that came immediately before. They were missing the bigger picture, the wider context of the full sentence. And of course, that very weakness is what set the stage for the next massive leap forward, the age of deep learning. This is when machines finally started to understand context in a much, much deeper way. So along came neural networks, and specifically these models called LSTMs, which were a total game changer. The amazing thing about them is they could read a sentence one word at a time, while holding on to a kind of memory of what they'd already seen. This meant they could finally connect the dots over long distances, like figuring out that a pronoun at the very end of a sentence refers to a person mentioned way back at the beginning. And the best part? The network figured out which connections mattered all on its own. And then came the transformers. This is the architecture behind famous models like BERT. Their secret sauce is a mechanism called self-attention. Now, just imagine for a second. Instead of reading a sentence from left to right, the model can look at the entire sentence all at once. It's like it can draw lines connecting every word to every other word, figuring out which ones are the most important to each other. This gives it a deep, holistic view of context that was just unimaginable before.
So, what's the result of this entire incredible journey? Well, today's modern transformer-based taggers hit over 97% accuracy. Just let that sink in for a moment. 97%. We've gone from clumsy handwritten rules that broke all the time to systems that can understand the tiny nuances of grammar almost as well as a person can.
And it's so important to remember this isn't just some abstract academic thing. This whole story, this evolution from simple rules to super complex neural nets, is directly powering the technology that you and I use every single day. This timeline here really just lays out the whole story. You can see it clear as day. Back in the 60s, it was all about human experts, linguists literally writing down grammar rules. Then the 90s hit, and boom, we get the rise of statistical models that learn from data. The 2010s brought the deep learning revolution with neural nets, which brings us right up to today where we're dominated by these massive transformer models.
And this chart, it really captures the core trend of this entire journey. Look at that. The amount of manual human effort started super high and then just completely nosedived. And at the exact same time, the machine's ability to understand context and its accuracy just went through the roof. It's a perfect trade-off. Less work for us, way more intelligence from the machine.
So really, the next time you ask your phone's assistant to schedule a meeting for you, or you type "book a flight to Boston" into a search bar and it just gets it, you are seeing part of speech tagging do its thing. It's the silent, unsung hero of grammar working behind the scenes of our digital world.
And all of this leaves us with one last really big question. We've gotten incredibly good at teaching machines to label the building blocks of language, with near human accuracy. But does knowing all the parts of speech mean the machine actually understands the sentence? Does it grasp the real meaning? Well, that's a question for the next big chapter in the story of AI.